Okay, yeah, thanks a lot for the introduction, Carlos. Like we said, yeah, it's going to be a bit an afternoon of introductions, and the goal is kind of that all of you have you will get a bit of an understanding how all these different software components work together, and also so that you can know what this could mean for a climate or a weather model. And then tomorrow and then the day after tomorrow we will get a bit more into the meat of dusk and dawn, and then we'll do a bit more interesting things. But yeah, let's just get started with dawn right away. So we want to give you an introduction, show you a bit the motivation, the history of dawn, and then also the future. So to start off with the motivation, for climate and weather models, usually that starts at the equations, and then these equations, the physical equations that govern our weather, they get discretized into numerical discretizations. So such a discretization is what we see here right now. We have a psi field, and we take the difference of that psi field at two different locations, and then we divide here by this L hat term to get an approximation of the gradient of this psi field. And that's kind of where our software starts right now, because in papers these discretizations and schemes are worked out by very, very smart people. And then that's kind of what we want to run on the machines. And in this form, unfortunately, this is not what we can run yet. So we need to actually go one step lower and actually write code based on these equations. And what this looks like is shown here. So here's a, let's say, straightforward implementation in Fortran. We can still see, so the original equation is visible in here. There's this these two side terms that are take the difference of, and then we divide by this L hat term, and we store this into this grad psi field. So that's still visible. What was added on top is two loops here. So once we loop over the vertical domain, we go through all levels of our atmosphere, and then for each level we iterate over the whole surface of let's say a globe, or maybe of a limited area, and then we carry out this computation for each of the cells, and we add all these indices here to this equation. However, this kind of works well if you want to run this on one single machine. Once you want to run this on multiple machines, things get more complicated, because then we want to take, let's say, the globe and subdivide it into separate patches, and each of those patches we would want to run on a different node, and then use MPI to exchange halo information between these nodes. And for that, we need to add another loop nest to iterate over those patches, get some indices, and we get a third loop nest here, and then we get a whole lot of more indices here, and our expression starts to get a bit bigger. So that's nice and good. It runs now on multiple nodes, and we can use very powerful HPC systems with thousands or maybe even millions of nodes. However, this is not very efficient if you have a multi-core CPU. So if you have a node that has multiple cores on it, let's say 16 cores, then you can run 16 MPI ranks on this machine. However, they will do all the halo exchanges through MPI. But all these 16 cores, they have access to the same main memory. So the memory is already shared between those 16 cores. So there's no need really to do these MPI exchanges. It's mostly redundant. And to be able to efficiently use this shared memory, we can add OpenMP directives, and then we run not a single MPI rank for all the 16 nodes, but one for one node, and on all. So we wouldn't run an MPI rank for each 16 cores, but one for one single node. And then on every single node, we can spawn multiple OpenMP threads to make use of all these 16 cores. And to get that, we will add these OpenMP directives to guide OpenMP to parallelize this code across our cores on a single node, and then we can save these MPI exchanges, and we can properly and efficiently make use of our shared memory. And so now we have these directives, and it runs well on multiple nodes and then on multiple cores. So we kind of get a bit into the current hardware architectures, and that's really nice. However, hardware architectures, I think that's an important term these days, because one really important hardware architecture that has been emerging lately has been GPUs. They offer very good performance based on their cost and also on their energy efficiency. They're very good in these two aspects, and they can often be a very attractive hardware platform. However, our original code doesn't run on them, and to make this code run on GPUs, we can add ACC statements, which we do here and here, and we add directives to decide whether we want to use ACC or OpenMP to accelerate this code onto our respective hardware architectures. And next, it turns out that we also want to change the loop order, because one loop order is good for CPU and one is good for GPU, but they're somewhat mutually exclusive. And to solve this, we add here another ifdef where we exchange the loop order here. And depending on our define here, we can switch the loop order. And now it works well on GPUs as well. So that's kind of where we are now. We have code that works well on all these hardware architectures that we are interested in. We can run it well on very high performance supercomputers. And we started off originally with kind of this numerical discretization. And let's say if you look closely, you will see that it still exists in this code, right? There's still these difference that we take and we divide by this L hat and then store in this gradient field. However, there's a whole lot of other things that came on top of it, from all these loops and all these indices here that weren't in the original equation. And the issue is that, well, what if our requirements change? For example, we want to approximate this in a different way, for example, using a higher order scheme. Then, well, on the equation, on the level that we started with, so changing this here on the left-hand side is kind of fairly easy. We can express this fairly concisely. But once we want to implement this change into what we ended up with here, things get very difficult. And the reason is that, firstly, the ratio kind of between the original equation and all the code lines that are added to support different hardware architectures, the ratios just kind of become very unbalanced. And then next also, these kind of the original equation and the optimization aspects for supporting different hardware architectures are completely intertwined. So, for example, our psi fields, they contain now all these indices, and they are dependent on our loop structures and our memory layout, and it's if you want to make changes here, you have to be very careful that you don't break things around here. And then the issue is, what if we want to support another hardware architecture? And I think this is there's some very interesting developments these days, where I think it's no longer CPUs versus GPUs. Now we have vector machines as well. An example is Fugaku. Currently, I think it's the leading supercomputer in Japan that has something in between CPUs and GPUs. And then there's people that are experimenting with FPGAs. And then there's very, very efficient tensor processing units coming on the market in the machine learning sector that promise very high efficiency with respect to cost as well as energy. And who knows, maybe in 50 years we will run our models on quantum computers. I mean, this is a bit of a crazy thought, but my point is that the hardware architectural landscape is starting to get very kind of exotic, and I think it's not going to become simpler. I think it's just going to get more complicated. And then also, for example, if we want to change the meshing library, so all these indices and the memory layouts, they're all dependent on the meshing library, and then it's very hard to do this with this form of code that we see here. And that's kind of, well, the motivation for Dawn, and the answer to that problem from Dawn is that you start off, well, again, with this numerical discretization, and then you express this as close to the original form as possible. So you kind of want to express this in a pure way, and preferably close to this high-level representation that we have here, and that's kind of how it's expressed in Dusk. And then we can use Dawn, and we can tell Dawn, well, please optimize this for OpenMP, and Dawn can give me an OpenMP version here. And then we can also ask Dawn to give us an OpenACC version, and Dawn kind of converts this high-level representation and fills in all these details that matter on these hardware architectures, and it adds all these things that we need to make it run on these different hardware architectures. Also, a note on disclaimer here. So these Fortran examples here, they're really just examples. They're for illustration purposes. There's actually no Fortran backend in there. However, Dawn does allow to add a Fortran backend. And I think if someone is interested in that, then I think we would also be interested to collaborate on this. And then next we can also say, well, we want to create C++, we want to generate C++ code that runs on GPUs. And Dawn can do that for us, and kind of, yeah, we have a sense of encapsulation here. Now I want to say a few words on Dawn's history. So Dawn has an integrated frontend called GTClang. This is a domain-specific language that's embedded into C++. And it's feature complete with respect to the requirements of the cosmodynamic core. And it's based on finite differences generally. The Dawn also supports a wider array of optimization strategies. It has various backends, a C++ naive code generation backend for kind of easy understandability, and then let's say for debugging. Then there's two Gritus backends that target either the multi-core backend or a GPU backend, and then there's a pure CUDA backend. So there's already multiple backends, and this kind of works out fairly well. So Dawn was used to translate the complete Cosmodi core. This includes advection schemes, diffusion, and tridiagonal solvers. And it does perform fairly well. So it does provide better performance than previous efforts based on other DSLs, with while kind of allowing for much more readable code. And there was a paper published on this where performance was compared, and you can see compared to the Stella die core, Dawn was always at least as good, and in some cases there were some very strong improvements that we saw in Dawn. So that was fairly nice. Now I want to give you an introduction to the design overview. So I think this is this to give you a bit of a high level overview of how these components play together. So Dusk is a front end to Dawn. I will say a lot more about Dusk after the break. And Dusk produces something called SIR. SIR stands for Stencil Intermediate Representation, and that's kind of the input format that we can feed into Dawn. So I think SIR it's kind of the interface. It's like the specification for the input format. So it's kind of an interface intermediate representation as well. So the stencil IR is kind of what we can use as interface, and that's what's being fed into Dawn. Dawn is kind of in this. It's split into an optimization component and a code generation component. They communicate with something called IIR. This stands for internal intermediate representation. So this is kind of an internal intermediate representation, internal to Dawn. And that's kind of also what separates the optimization and then the code generation part. And in the code generation part, well, if we want to target a C++ CUDA backend, then the code generation component can produce C++ files that we can compile with GCC and then get a binary object, as well as producing CUDA files that we can compile with NVIDIA CUDA compiler, and then we get binary objects. And that's kind of the current architecture of Dawn. And the good thing about this is that it's modular, and we can add new components to this. So firstly, we can add new front ends that produce SIR, and as long as it respects this interface here, it should work out fairly well. And next, you can also hook in your own code generation framework. And as an example, you could create a code generation framework that targets to that aims to produce that generates human readable Fortran code, which then can be compiled with a Fortran compiler to get a binary object. And I actually want to stay a bit with this slide for now, because I think it kind of highlights fairly well how the issues are solved that we started off with when we looked at our motivating example and this Fortran code. And what you kind of can see is that if we want to support new hardware, what we have to do is we have to add a new code generation component. And this code generation component, it will work with this internal intermediate representation, with this IIR. And in this architecture, this concept of adding support for new hardware, it's encapsulated away from all the other parts, from the components that take care of expressing the high-level equations, from the component that does optimizations. It's all nicely encapsulated away, and it's interfacing the other components with this kind of well-defined interface. It's kind of still in development, but it's still fairly well-defined, this interface. And with this encapsulation and these interfaces, what we gain is we gain modularity, because before we had all these aspects were interleaved, where indices were part of the expressions of the equations, and the loop, the loops they were kind of right next to each other. And in this architectural overview, you can see how they're nicely separated, encapsulated, and they communicate through well-defined interfaces. And what we gain out of this is modularity. And modularity allows us so much flexibility, where we can exchange our components, and we can reconfigure our architecture in very, very flexible ways. That's almost impossible when you have this highly coupled code, where all of your aspects and your separate concerns are so highly coupled. And you can also see this with the front end, right? We have Dusk, which works with Dawn, and GTClang is another front end, and they all target this interface, and you can have your own front end that targets this interface. And then the optimization aspect, it's kind of separate from all those as well. So you no longer have all these optimization aspects that are part in your original equations, and it's, I think that's just this architecture allows for the separation, and it kind of gives us a lot back that we lost by the previous approach. And I think it's important that we since basically back in the days, we could just build something for CPU, and we would buy a new CPU that was twice as fast, and our code was twice as fast. Now the machines, they get twice as fast too, right? The top supercomputers, their speed develops so crazily, but we don't get this for free anymore. We kind of need to adapt our approaches to benefit from these hardware power increases. And I think this architecture could be one approach to really regain this. And here, and with such an architecture, we have to pay a lot less than we had to do with kind of let's say the traditional approach. So next, we can have a look at the actual SIR. So SIR it's an abstract syntax tree. It's fairly close to the DSL level, so it's kind of a higher level IR. It's fairly close to the stencil language. It's an interface for different front ends. This format is well suited for translation, and it's not really meant to be human. It's not really targeting humans. This is kind of meant for our translation. Then next we have this internal intermediate representation. This is also a tree-like representation based on ASTs, and it contains many more details that were collected during analysis passes. This format is very well suited for transformations, for example, through visitors. And compiler passes, basically, they will transform valid IIR, input IIR, into valid output IIR. And if we look a bit more closely, what we have is we have at the top there's a hierarchical compartmentalization of ASTs to achieve valid parallelization. So there's a bit of a hierarchy of different parallelization aspects. So in this example, let's if we take the targeting a GPU into consideration, then this kind of multi-stage roughly corresponds to a CUDA kernel, whereas these stages and do methods, they roughly correspond to iteration spaces. And they're kind of, there's a bit of a hierarchy of different parallelization aspects, and then optimization passes can work with that, and depending and do these transformations depending on what they want to optimize for. And then also this ASD is very decorated. There's a lot of more information in there from analysis passes that the optimization passes then can utilize to make good optimizations. So a few words on Dawn's current state and the future. So we can translate most of the computations in the Icon Die core. So we're roughly 90% feature complete here with respect to the requirements of the Icon Die core. We haven't translated it yet. However, we already translated quite a few isolated computations. They're translated and they're running in end-to-end tests, and that this is working out well so far. And what's currently under development is adding support for global values and then horizontal subdomains such as nudging area, halo, interior, lateral boundaries, and so on and so forth. So in the future, we want to further close the gap to Icon. So that means kind of mostly horizontal indirections for semi-Lagrangian schemes. And we want to start to translate whole Icon modules, for example, the diffusion component. And that concludes this introduction to Dawn so far. I hope we could clarify some or give you a more clear view on what Dawn actually is and how it tries to solve these issues, the 3PP problem, for example. And now we have some time for questions. So for the questions, we have this Google Doc. I think there's a link in here. Maybe I can post this in the chat again. Yeah, I think I'll stop sharing for now.
Thanks, Ben. So thank you very much for the introduction to Dawn and Doc. Are there any questions? Remember that you need to go to the Google Doc and write your question there so that we can bring it to the speaker. It's totally fine if it's like very basic questions. Remember, we are switching a little bit context to a different DSL, so that's totally fine. It's important we clarify basic concepts, actually. I'll give some more time. There are some people writing.
Yeah, absolutely.
There is a question.
Sorry, yeah.
There is a question from Remo asking why are there two IRs in Dawn, two intermediate representations?
Yeah, I think that's a good question. The reason for that is because these IRs they serve two different purposes. So SIR, the purpose of SIR is kind of to be an interface for a front end, and the idea is that it should make it easy for the front end to generate this SIR. And the purpose of this internal intermediate representation is to be good for optimization transformations. So it's a bit lower level. It contains some more details. There's analysis passes that happen that when we convert from SIR to IIR, and these analysis passes will add more information. Some of it may even be redundant. But IIR is really kind of the purpose is to be suitable for optimization transformations, whereas SIR kind of tries to make it the life easier for a front-end developer, so that you don't have to run all the analysis yourself, and Dawn can take care of this.
Thanks, Ben.
I hope that clarifies it. Otherwise, please ask more clarifying questions as well.
Mm-hmm. Another question was coming from Rainer. He was saying that he found the Dawn repo on the GitHub. However, he could not find the Dask repo. Is it publicly available?
Absolutely. Maybe I can share the link. Here it is, and I can write it in the chat, which is here, and maybe we can add it to the Google Doc as well.
All right. Thanks, Ben. Then another question from Will. Do I understand correctly that you have no plans for a Fortran backend?
Yeah, that is basically correct. So we at ESiWACE we're strongly targeting GPUs. That's what our machines have, and that's what we focus on. I think it would be cool to have a Fortran backend, but yeah, with resources it's a bit hard to make this work, and we're really more focused on the C++ GPU backend. Nevertheless, I think we would be interested in collaborators if other people would like to investigate this.
Okay, good. One more question. Not sure I understood from G. OpenSSC backend does not require NVIDIA Unified Managed Memory. It knows which arrays are present on this device. I think he's asking like how does OpenSSC knows whether the array or the data is present on the device. That's probably more like an OpenSSC question, right?
Yeah, to be honest.
I think there is explicit data management with the OpenSSC model, so you just have to instruct with OpenSSC just to send data to the, and then it's going to be, and you can also explicitly say when it's going to be present, so it's very explicit model. All right, maybe one last question from Rupert. Do you think you could use Cyclone Fortran backend via translation from IIR to PsyIR? So whether you can hook into the PsyIR and then use the Cyclone Fortran backend?
That's an interesting question. I don't know PsyIR that well to give a very well-informed answer to this question, but if it's just about possibility, then I would say it would be possible to make this work. I'm not sure if it would be that reasonable. I think you have to be careful because some optimization passes, they could kind of interfere with each other. So I'm not really sure how reasonable that would be, but I think in theory it should be possible. Yeah, so I think it depends on what you really want to gain from this, and yeah, also I don't know PsyIR that well to really give a thorough answer here.
Thank you very much, Ben. Then I think there are no more questions. Thanks a lot everyone for asking the questions and making this interactive.